Today's presentation is part of our programming series. It's one of 3 sessions, so hopefully by the end of it, everybody will have a solid understanding of programming. Today we are joined by Justin and Mannit. They are from IHOT Robotics, and they're doing an introduction to FRC control systems. So let's get them going.
Yeah, so like you mentioned, we're just going to introduce control systems in the context of FRC today. And then briefly who we are. Again, we're from IHOT Robotics from the Atlanta International School. And then you can contact us at that link if you have any questions afterwards. Yeah.
You can follow along with the presentation using the link or the QR code. We have a lot of code snippets and examples throughout the presentation, even some resources to use at the end. These are really helpful, so if you want to follow along or use that later, you can just use that link above. Some of the topics we're going to be covering is mostly around using control systems, specifically in FRC. So we talk about what a control system is and why it's important. We're going to give some examples of teams using it and good and bad ways to use control systems. We're going to go into the different types of control loops. We're mostly going to focus on open loops and closed loops, which are bang-bang control or PID control. We'll also talk about how to use Talon SRX to program and write efficient code to do stuff like motion profiling, motion magic, and other, and we're going to give some resources so you can use later on for your teams.
Yeah, so again, most of the things we're going to cover today are like the, I guess, practices that we've found worked best for us. But there are, of course, like just a bunch of different ways to do the things we're going to talk about. So now we're going to discuss briefly about like why do we use control systems and like why do we need them. So again, like automation is a huge factor in robotics, not only in your autonomous period, but also in teleop, because if possible, you want to reduce the burden on your driver as much as possible, right? So any level of like automation you can add to your robot will pretty much increase the performance of your robot in terms of like the ability to drive it. And then it can also account for like unpredicted behavior if you use control systems. And then it's really good to use control systems for mechanisms like arms and elevators, just so you can have a precise control over the position of the mechanism. And then you also have things called like velocity control. So let's say you have a flywheel on a shooting mechanism. You can control the velocity of the flywheel to basically get a consistent shot every time. So now we have 2 examples of control systems. So the one on the right is from 254 during their 2016 season. And if you notice, like for that season, you basically had a goal, and then you had to shoot a boulder into the goal. And for their mechanism, they decided to use a turreting like shooter, and that basically allows them to maintain like consistent aim throughout the entire motion of their robot. So you can see how their drivetrain is rotating on the ground, but their turret is using a control system to maintain the aim to the goal. And then like there isn't just a need for control systems, right? You need to tune it well and everything. And the one on the left is just what happened when we were tuning our control system for our autonomous. So obviously that's not what it was meant to do. So it's really important not only just to like write your control systems well, but also tune the gains well. And we'll discuss those 2 topics later as well. So this is just a video from 971 in their 2014 season, and it's a really good, I guess, demonstration of control systems, and we'll break it down after we watch a little bit of their reveal. Yeah, so for their robot that year, like not only is there like a control system for rotating their entire arm back and forth, but actually the individual, like the top and the bottom of the claw is controlled separately, right? So if you can imagine, if you have a poorly tuned system, their claw will separate as it rotates, and they had an issue with that, right? 971 is a really good team in terms of software, and that's why they were able to make a design like this. So basically they had to keep the bottom and the top of their claw in sync throughout the motion in order to maintain grip of the ball. So that's a really good example of advanced control systems. But today we're gonna go into like, I guess more of the basics, but eventually it should lead up to something like that.
So here's another example of a situation where you'd use control loops and where it's not using control loops. On the left side, you see the same robot trying to climb, and in this case, it's trying to basically go to a certain step for a certain amount of like a distance, or in this example, use percent output. So it would just basically give a certain voltage to the motors to make it climb, but it doesn't stay there. It starts to sink back down. You can also see in both situations, they're running at the same speed if you watch the status light. But on the right side, it's much faster because it's using the max velocity and max acceleration to basically get to the point in the most efficient way possible. We're going to talk about more about this later with motion magic, which is what we used on the elevator. Another thing that's really good about control loops is it's very repeatable. So you know where the arm is, you know where the elevator is, and you know the drivetrain of the robot is. So when it's climbing, it's going to climb to the same position every single time. On the left side, if it's controlled for a certain amount of distance, it really depends on its surroundings, and it doesn't take the feedback or the sensors into consideration. So the one on the left is more of an open loop.
Yeah, so now we're gonna break down like how a general control system works, and then we'll go into different types of control systems later. But basically, with a general control system, you have something called a set point, and this is normally your like desired target. So like for a robot, it can be like the position of your elevator, or it can be the angle that your arm is at. But then it can also be like the velocity of your flywheel, or even like something we use every day, like a thermostat. You have a set point, right? It's the temperature you set. And then you have something called the process variable. And the process variable is the variable you're kind of repeatedly measuring. It's like, so you get that data back from your sensors. So like, for example, with an arm or an elevator, you can use an encoder, for example. We'll talk about different sensors later, but that can measure rotations essentially. And we can use that to calculate the error between our current point and our set point. And that's the error you see in the beginning of the control loop. And then yeah, so that's just the difference between your process variable and your set point essentially. And then once that is calculated, so it can be like the angle difference from your set point in your arm, or it could be like position error in your elevator. Once that's calculated, we feed that error into our controller. So that can be like different types, we'll go through them later. But that controller, the job of it is to basically take that error in and then compute some output that we can send to the mechanism to correct that error. So you can see in like a general control loop, the goal is just to eliminate the error in the system between your measured value, your current value, and your set point.
Here are a couple of sensors that we used for getting inputs from the robot. We use encoders to get rotary inputs. So basically, we can use mag encoders, which work with Talon SRX, and either have relative or absolute values. We're going to talk about more in the motion profiling side. But we also use for our drivetrain Grayhill encoders. For vision, we use there are basically different ways you can go about this. We've used COTS parts, which is basically commercial parts like PixieCam and Limelight, and these have the ability to train them to look at a certain color or a certain shape and recognize it. So then next time it sees it, it gets all the values for it, like the angle from the camera, the distance from the camera, and this is useful to use as an input for the sensors. You can also do this in a custom way where you can write your own code using OpenCV or by connecting a USB camera to a Raspberry Pi. If you look at the 2017 game, if for a live shooter like our shooter would basically have to detect the reflective tape on the shooting, like wherever the ball has to go, where the fuel has to go. So what we would do is we'd use a camera with an LED around it to get the same HSV, the color of the reflective tape, and it would basically find the angle from the reflective tape and move to that angle, so you know that you're lining up right. It can also use a smartphone camera like a Nexus, which some teams use, like Cheesy Poofs, like you saw.
Yeah, and then just to reiterate with the vision, So some teams will actually use your camera or whatever type of system you're using as a feedback sensor. So like we said here, you're using a sensor to measure your process variable. But we actually don't recommend that you use a camera as a feedback sensor. The reason for that is because a camera has a limited frame rate or refresh rate. And then it's not good to have such a low refresh rate when you're running a control loop. So what we actually did, like Mannit was saying, we used the camera to detect angle difference, and there's some math you can do to do that. And then we send that angle difference to our gyroscope. So you can also use a gyro and IMU. So we personally use the NavX, and what that does is, one of its features is allows you to detect basically the relative heading of your robot. And then so we use the angle difference we get from our camera, and then we use a control loop running against our gyroscope in order to accurately turn to that angle difference. So with the 2016 example for 254, you can imagine how they're doing something similar. They're getting the difference in the angle from their turret and their goal, and then they're using some sort of sensor to run a control loop on, which can get their mechanism to rotate to the right position. Another alternative to the NavX is a product offered by CTRE, or Cross the Road Electronics. So most of our electronics are actually from them. But they have something called the Gadgeteer Pigeon IMU, and that's, again, another type of IMU. That particular one can interface directly with the Talon SRX, or like a CAN bus. We'll go into that later. And then there are also different types of limit switches. So this isn't really used for closed loop control. It doesn't really give continuous feedback to your system. But it's really good just to have limits on your system. You don't want to have an elevator drive into itself, for example. You don't want it to go past its limits. So you can use the micro switches, which are included in your kit of parts. But then you can also use another type of sensor. So CTRE also offers something called the Talon TAC, and that's basically a contactless limit switch. And then, of course, there are different types of other sensors. We have ultrasonic sensors, Hall effect sensors, and then just a bunch else. And that all, if you use them all together, it can really help when writing your control systems. So this is the shooter arm from 971 in 2016. So it's the same game as the 254 robot, but you can see how different their approach is with their robot. But one thing that is similar, though, is that they still have a lot of use of control systems, right? So with the 254 robot, you have the turret that they probably ran a control loop on. But with this, they have kind of this 2-linkage arm system that they use to shoot over robots. So they're not height limited. And then you can kind of see where they would use control systems in this case. So they would need a separate control system for the first part of their arm where the shooter is, also the kind of the joint that goes up. That's another control system. And then they also use, they have an intake that drops down to pick up the balls. And that again is another control system. And then one thing that's important to note about this is basically in their configuration, it's, if you do normal control systems just normal PID loops, it's actually really likely that your mechanisms are going to hit each other and they're going to run into each other. So what they had to do for this is something called motion profiling, and we'll get into that later. But what motion profiling does in basic terms is it basically gives you acceleration graph over time. And that allows you to know the exact position of your mechanism at a certain time. So they can plan that, so when the robot unfolds, it doesn't really hit the other parts of its mechanisms. If you run a PID loop, then it'll just jump to it as fast as possible, and it's probably going to run into its intake, for example.
Yeah, another similar example is the 254 2018 robot. This was the Houston World Champions this year. They use their elevator and arm very efficiently using motion magic or motion profiling again. So they have, their arm is basically similar to the previous example, where it has a double joint, and they have to kind of control that and avoid hitting the elevator, but also they have to avoid hitting game pieces like the scale. As you can see on the example on the left, they're able to move their elevator up and time their arm to come out right above the scale point, which is also used for switch, and they have a cube pass through so they can shoot above and over the robot. So having all these set points laid out is really important because there's no, the driver basically a lot of the problems go away from the driver, so the driver doesn't have to worry about controlling it. They basically have set points and it goes to that position and it's repeatable. It does that every single time they click a button and it goes to that exact position. So it's really efficient, it's fast, and it ensures that there's not a lot of problems during the system. You can also see on the elevator, basically, to get to these points, they have encoders on almost every single joint that they have just to make sure that it uses the feedback and then runs the control loop properly.
And then this is just briefly about like sizing your system. So like this isn't the main focus of the presentation, but basically what we wanted to say is that if you don't design your mechanism well, a control loop isn't gonna fix it. Like a good example is like, if you remember us from 2016, we had this really bad robot, to be honest, and we had this giant, like really heavy arm that was powered off a gearbox, and it was not calculated properly at all. It was just a random gearbox that we threw together. And then with that, it was very difficult to tune your PID loop, right? Because just how it's designed. So what we suggest is like, you just ensure like, you can find the power specifications of your motor and just ensure that it has enough torque to operate your mechanism at a certain speed. And then you can use the JVN calculator to do that. If you haven't heard of that, it's just a calculator you can get online. You can search it and it'll pop up. And that just allows you to size your system. And then one more thing is like 8 to 10% stall. So if you use 8 to 10% stall of your motor, you'll end up with a high reduction in your gearbox. So like if you have a versaplanar interior or something, it's really easy to do that. And then with that, your frictional force opposes your gravitational force. And then for our elevator last year, actually, if we manually move our elevator to a certain position with our hands while the robot's off, the reduction is such that the friction basically overcomes the gravity. Like we lift up our elevator and it stays there by itself. So if it already does that, if your mechanism is basically just staying by itself already, without a control loop even running on it, basically you can use a control loop on top of that just to get your precise movement, but then also just like make the motion smoother. And that really helps when you're tuning your gain. So like again, the mechanism is important, and then you can think about adding control loop on top of that.
So one thing that we've talked about a lot and we're going to go into is using Talon SRX. This is basically a speed controller provided by CTRE, which we use. And the great part about this is it has onboard control loops built in. So if you download the Talon SRX SDK into your like WPI lib code, into your robot code, you can basically run different control loops straight from it very easily. We'll show some examples later on. But a couple of things it can do is percent output, which is basically what we use most of the time in teleop for just applying certain voltage. It's also called percent voltage, and that's like a number between -1 to 1, and it applies that much voltage to the motors. Then there's position. You can use the encoder's feedback and actually set it to a certain position, and you can run different control loops with that. There's also velocity, for example, flywheels, being able to change the velocity of the wheel for a shooter. You can use the power distribution panel and get the current and basically control the current of the motor, and then you can have a follower. So if you have to just do a simple function as in move in straight, then you can have a right motor go at a certain percent output and then have the left one follow, or use any control loop on one side and just have motors follow it. And it's the same thing. And next we would also use motion magic and motion profiling, which is, we're going to go a lot into this later on, but CTRE provides a really good way to do motion magic right into the code with just once you've tuned your PIDs and once you set your set points, you can use motion profiling really easy.
Yeah, so just to clarify really quick, motion magic is just what they call their tool to automatically do motion profiling. And we'll go into that later. And then also, if you guys aren't already using the Talon SRX, we highly recommend it just because it makes your life in terms of control systems so much easier, because all of it's kind of like on board, and you don't have to necessarily write your own motion profiling code if you don't want to. So it also, Mannit will go into this, but it can take in sensor data directly into it.
Yeah, and the great part about this is it can run those sensors at really high refresh rates. So if you have an encoder, for example, and you wire that straight to the Talon SRX, in the code you can use the encoder as an input, and then send it to the control loop or whatever one you're using, like motion profiling or a set position, and it uses that input and basically constantly uses that as feedback. So when you're doing this, it's a really good idea just to have this built in with make sure that your sensors work with your Talon SRX, and make sure that your code also uses these really well. You can also go on the RoboRio online dashboard and set up different PID loops or even different control loops, and then program those in the code to use just a certain ID, so you can do your PID and test them in real time.
Yeah, and then also this port on top, the kind of like where the two screws going into the speed controller are, that's a port you can use, and it's called the Gadgeteer port. And if you buy like a CTRE based sensor, then it'll connect directly to it. But if you don't buy something like the SRX Mag encoder, for example, you can use a breakout board, and this particular board is one offered by AndyMark, and it allows you to connect basically pretty much any sensor to the Talon SRX, and then you can use that as a closed loop control.
So now we're going to start going to a couple of different control loops. The first one we're going to look at is open loop. This one does not use any feedback from sensors, so it's solely based on a certain desired input that you give it, and the example below shows a heater or like a dryer. For example, you'd give it a certain amount of time, say 30 minutes, and it would dry it for 30 minutes and then switch it off. This does not take any actual input, so it doesn't actually know if there are any variations in, say, the voltage, the momentum, if you have a robot, the momentum from driving, or even any unpredictable behavior. In last year's game, for example, you would see a lot of times where robots would just try to drive straight and cross the baseline, but since the autonomous is so dynamic, it could actually come and hit, another robot could hit you, and making sure that you come and you use sensors and feedback is very important, but open loop does not do that, so it wouldn't be a good thing to use in that scenario. If you also look at an open loop example, so you can see that the robot on the bottom is basically trying to go straight, but it's basically setting both sides of the drivetrain to go straight for a certain voltage, but you can see that starts to curve left because there's so many other variables that it doesn't take into account. For example, when you're doing, the mechanics aren't always perfect, both sides are not always evenly weighted. There's the friction from the ground. There's also the other robot in the center. If that were to hit the robot, it would actually lose control and go in a different direction, which could alter the way the game is played. It also, you have to, sometimes if you want to be more accurate with open loops, you have to actually reduce your speed, which isn't efficient. So there are a lot of reasons why you would not want to use open loops when writing code like this. Places where you would use open loops were just if you had to just, for example, in our intake, just running the intake wheels to basically intake a cube. If you have to run that at a certain speed for a certain time, you can just turn it on, turn it off based on teleop control. But then again, when you're automating things, it's not a good idea to use open loops.
Yeah, so it's basically not precise and not repeatable.
Yeah.
Yeah.
And here's an example of writing it in code. This is Java code of an autonomous periodic. It's kind of like the example that you previously saw, where if a robot is driving at 10 feet per second, then you just write it at 100% speed. So you'd set it to percent output of 100%, wait for 10 seconds, and then switch it off. That's not the most efficient way to write code, but or to control the robot, but that's how it would be done if it were to be used in that scenario. So if we were to use this, but then bring in sensors into it, we would have what's called bang-bang control, or on-off control, or hysteresis control. All of these it's the same thing, but essentially takes encoder or any kind of sensor value and has two set points. So you'd have a maximum set point and a minimum set point, and it would basically stop within that range. A great example is a thermometer, like a thermostat, like Justin said before. What a thermostat does in your house, for example, would basically turn on the thermostat until you reach a certain temperature. Say your desired temperature or your set point is 68 degrees. When it would hit 70 degrees, it would turn off. So then it would start to cool down, and then once it hits 66 degrees, it would turn on. So it would always try to stay within that range. So your temperature would constantly be in that range, but this also brings up problems with accuracy and also speed. If it's just on or off, it's just two states, so you're never getting more accurate over time. It's just trying to get from one point to another. An example of a place where you would use this is if you just had to go straight and stop, like the previous example. You could do this with your angle using the Navex as an input, and then also do this with your encoders. So you just go straight and make sure that you're driving straight into a certain position. It wouldn't be as accurate, and it wouldn't always take in. It would take the feedback, but it wouldn't always take into consideration different variables around the robot.
Yeah, and then the problem with this, like Mannit said, is like you have a deadband unless you want oscillation. So like you have a large range that the system can be in when it stops. But once you reduce that deadband with the bang bang controller, then you start to get oscillation. So like your robot, let's say you need it to go like, I don't know, 10 feet forward again, like, and then you set a range like 10, like your robot's never gonna end up at exactly 10 feet, like 10.0000. So it's gonna just oscillate back and forth.
Here's an example of bang bang control being used. So if the set points in this case would be 3,000, if it's within 3,000 to 4,000 encoder ticks, it would basically start or increase or decrease the speed at like either 1 or -1. So there's no variable taking into consideration. And also, once it would be within this, so anytime it's within 3,000 to 4,000 encoder ticks, it would stop. So that's not always accurate enough for a situation where you're doing autonomous to go to a certain point, especially when you have multiple turns and decisions being made, like driving around the scale, around the switch, going towards the scale. Doing this multiple times would increase your inaccuracy by a lot.
And then let's say you use this for a driving example again. Even though we're technically using a control loop now, just to move forward, it doesn't guarantee you're gonna go straight, right? Because it only measures the encoder outputs. It doesn't take into account like a gyroscope that might be on your robot, for example. So like your encoders might reach their target position, but that doesn't necessarily mean you're going straight. Like for example, your right side of your drive could be faster still, and it'll cause you to turn, but your left side will eventually reach its target's encoder tick as well.
One also thing to remember is throughout all these examples, you'll see that we use the Talon SRX. The left drive and the right drive is the Talon code, and basically they have a really easy way to set values, but in this example, you can see that they get the selected sensor position. That's basically getting the sensor that's wired to the Talon, and through your RoboRio online dashboard or through the code, you can just set it to a certain ID. In this case, is 0. Also, one thing to remember if you're going to use this code is the symbols for the greater side and left side should actually be switched, because once it goes within that range, it should stop. So it's the other way around. Yeah.
Okay, so basically those were control loops, but we don't really recommend that you use something like a bang bang controller for like most applications. So I guess in FRC it's really common to use a PID controller, and it's actually really common in industry as well, I believe. So what PID stands for is proportional, integral, and derivative, and basically those are the separate terms in your PID controller. And then with the P term, you can actually use that just by itself, just a proportional controller or P controller. And then what that does is, like with the bang bang controller, if you go over your set point, you go 100% back. If you're under, then you go 100% forward. What P does is it does exactly what it sounds like. It's proportional. So as you get closer to your set point, it proportionally decreases the output of the controller. So like, let's say we have an arm at 0 degrees and we want it to get to 45 degrees. As it approaches 45 degrees, the controller will automatically lower the output of the controller, so it'll kind of like go fast at the beginning and then slow down, and then it might oscillate at the point. And that can be used by itself, but there are some problems we face when using just a P controller, and that's like, in real life we have friction, right? So let's say you're decreasing your output as you reach 45 degrees. Let's say the controller outputs an output like 0.0001. That's not actually going to correspond to your motor motion, because there's friction in the motor. It's not going to move that slowly, right? It's just not going to respond to the motion at all. So that's a problem, right? Because then we get something called like steady state error, because we're always below it. Let's say if we have friction. So we'll never reach our set point, generally. And then, yeah, so that's why we introduced the integral term. And so what that does is, it's just integration. It like basically accumulates over time, and that removes your steady state error. So the problem with just a PI controller, though, is that when you have that, it does tend to oscillate, similarly to the bang bang controller. And then that's when you would add your derivative term, so the D part of the PID, and that's your derivative in this case. You can see in the equation there, it's just the rate of change of error. So basically, as your rate of change of error increases, you're oscillating, right? So what it does is it basically does damping on the control loop to remove that oscillation. And then you would tune your, you see on each term you have your K coefficient, so that's just your gain for the specific term in the PID controller, and then you have to adjust those correspondingly in order to tune your system correctly. So this is an example of a robot that's using a PID controller. So you can see how they're using it actually on a lot of things. They're using it on their drivetrain. So they seem to have a separate PID controller for rotating and a separate PID controller for moving back and forth. And then probably a PID controller for their elevator as well. And then so for the driving, for example, you would use your sensor, which is most likely an encoder on your drivetrain. And then you would run a PID controller, so you would have your set point is the distance you want to drive. And then the process variable, like we were talking about earlier, is measured by your encoder, and then it calculates the error, and then it uses the PID controller in order to determine appropriate output to deliver to the motors in order to travel that correct distance. Then for the rotation part, you see when it's turning, it probably uses a gyroscope. So like the Navex or the Gadgeteer Pigeon IMU, you can use those. Those are, they have gyroscopes in them. And then you can use them to basically measure the relative heading of your robot, and you can see the angle your robot's facing. And then you run a control loop. So let's say you want to turn 90 degrees. That would be your set point. And then you measure the error between your current angle and the set point. And then your PID controller computes appropriate output, again, to deliver to both sides of your robot in order to rotate. And then the same thing is true for their elevator, where they could have different types of sensors for their elevator, but for our elevator, personally, we did similar thing to our drivetrain. We just put an encoder on the gearbox, and then when it goes up, it rotates, and then we can measure our position of our elevator based on the revolutions of the encoder. And then again, you have the PID controller with your set point, which is a target encoder value, which would correspond to the height of the elevator, and then you would measure the current one, and then you compute the error, send it to the PID controller, and then it'll send your motors a certain voltage to get rid of that error. And then you can see how simple the Talon SRX really makes PID control. It's literally it really boils down just to one method call, so the dot set, right? But what we're doing here is we're configuring our P, I, and D gains. There's also F, which is something called feed forward. That's basically, it's something else, but for traditional PID controller, you don't need it. And then what we're doing is we're assuming the mechanism has two motors. So our motor B is so the Talon SRX has a dot follow method, like Mannit said, and that's just setting it to follow the PID controller running on the Talon SRX for our motor A. And then once we set our motor A, it actually makes you pass in a control mode. In this case, we're using position, so that's just running a PID controller on the position of the encoder. And then we are sending it a set point. So the set point would be the height in encoder ticks. And then basically that is abstracting the PID controller for you. And it's doing the same thing. It's calculating the error, and then it's feeding it to a PID controller, which then gives you back basically a percent output to send to your motor controller. Okay, and then so after PID, we have something called motion profiling. And then in terms of the Talon SRX, it's referred to motion. Well, they actually have a motion profiling mode and then a motion magic mode, but we'd recommend you use motion magic. It just makes things really easy. And then the problem with the PID controller is that it assumes your system can get from point A to B instantaneously. And we know that's not the case in a real system. With the motor, you have acceleration. And your elevator can't teleport, right? It can't teleport up to the right position. And PID controller doesn't, it assumes that it can. which is wrong. What your system actually does is it follows a profile, and you can kind of see a graph here where it's graphing acceleration, your speed, and jerk. And if you specify that profile of where your system can be over time, or should be over time, then you get a smoother motion instead of PID. Like, you know how like a BID can kind of like jump in place? Motion magic or motion profiling will accelerate your system, and then it'll decelerate as it approaches your set point. And that's really good, right? Because like with mechanisms, you don't really want like that really fast back and forth motion. You want it to accelerate and decelerate. It just expands the lifetime of your mechanism. And then also, as we mentioned with the 971 example with their shooter arm, this allows you to synchronize motion between your different mechanisms because you know where your mechanism should be over time. Whereas PID is kind of like jump into place all at the same time. And that can be bad, like where you have the unfolding intake like 971 did. Like if it just all jumps to position, then it's probably gonna hit each other, and that's bad, of course. And then with motion magic, again, that's just the specific name for motion profiling or a type of motion profiling that's on board the Talon SRX. And what that does is you specify like your cruise velocity, your like desired velocity that you want the system to cruise at, but you also give it some acceleration information. And what it does is it basically computes or generates that trajectory for you. So now we can look at an example. So that's our robot from last year, and actually pretty much all of our control loops use motion magic, besides our drivetrain, and we'll go into that later. But you can see how our elevator just accelerates to a certain position, then decelerates as it approaches the set point. And then same thing for our arm. We had an arm connected to our elevator, which was running a motion magic control loop using the Talon SRX again. And then you get a lot of nice properties out of motion profiling and motion magic, but CTRE makes it really easy again to do all of that. It really like abstracts the code and makes it super simple for like any team to get or use motion profiling. So here we see like an example of motion magic code, and it's slightly more complicated, but this is pretty much all you need to do. You just set your PID gains again, and then you configure like you set your like basic parameters of your mechanism, like your cruise velocity and your maximum acceleration that you want your mechanism to follow. And then again, we have a secondary motor here, and that's following the trajectory of the motion magic computed on the first Talon SRX. So you would have two Talon SRXs, but one would be following the first one. And then at the end, we just have a dot set method. And again, we pass in the control mode. We're using motion magic, and then you just give it a set point. And then that's it. And then it computes all of your acceleration graphs for you, and it follows that profile automatically. Of course, you need to do some tuning, but if you design your mechanism right again, like it was super simple. Yes?
So as far as the motion magic, is it learning the process, or I mean, what kind of parameters do you send to it, or does it learn, I guess?
Wait, sorry, what?
Well, I'm just trying to understand as far as, I understand the universal PID, but I'm saying as far as for the motion profiling or the motion magic, what is the process? Basically, it just understands how it's performing and then adjusts its performance accordingly, or?
No, so like it doesn't learn like you're saying. What it does is it's literally, you can think of it as a PID loop, but instead of instantly like assuming that your system can instantly jump to its target position, what it does is it actually takes in the physical constraints of your mechanism into account. So like here we have the extra like methods like configure motion cruise velocity, and we're configuring the maximum acceleration of the system, right? So now it knows that our system can only accelerate at a certain rate, and that we want it to hit a certain cruise velocity. So now it generates that profile, like that trapezoidal kind of shape we saw earlier, and then your entire system will follow that.
How
So
would you determine like max acceleration?
So
max.
yeah, so we kind of tune that along with when we tune our elevator, for example. If you go back to the example, you can see how when our elevator moves up, it speeds up and slows down, right? So what's really happening there is our max acceleration is when we're basically mechanically designing our robot, we know how fast the elevator can move at and how fast the drivetrain can
You
move
say
at.
the benchmarks as you're going.
Yeah, exactly. And then we have our cruise velocity is where our optimum speed would be, basically like an average of where we'd want to go.
Yeah, and then also you can, like if you do use JVN calculator like we were mentioning earlier, if you design your system in JVN, it'll give you some parameters as output, like what your expected velocity should be, for example, of your mechanism. And then we'll go into it later, but CTRE offers really good documentation for all of their stuff, and they walk through the process of finding those parameters for you. Like they even have example code. Let's say you don't even know the max velocity and the max acceleration of your system. They have example code that you can run, and then you can like experimentally find all of that data, and then you can plug it back into Motion Magic, and it'll run like you want it to.
So Motion Magic works great with elevators, arms, and things like that. But when you're using on a drivetrain, you also need to take into consideration the position. And we use Pathfinder to do this. So Pathfinder is a motion profiling library. What it essentially does is it generates a path specific to your drivetrain. So we used a tank drive, and you can see, for example, the black square in the next behind the cube zone is where our starting point is, and the red rectangle is where our ending point is to the switch. And it basically created a path between those two waypoints with our position, which could either be relative or absolute. That's more like when you're coding it, that's more of a preference thing. But when you're once it gets to the two waypoints and where the ending angle is of the robot's heading, it would basically create a path for it to follow. And if you can make these paths and design these well, then you can put them straight into the Pathfinder library based on putting each of the waypoints, and it'll generate the path in the code straight onto the RoboRio. Another great thing about that is you can actually download all your paths onto your RoboRio. So when you're running it on autonomous, it immediately runs whichever path you need for that situation. It worked really well with this game, for example, because you don't know what autonomous you need to run at that point. So when we preloaded each autonomous from each starting point to each situation, it would basically go and run that path once it finds out where the scale is and where the switch is. And it's also useful when you need to change a path during a game. For example, if you're doing a match with another team and you think that there's going to be a collision, you can change your path to basically go around them, and this would basically create a spline. And splines are nice because you don't need to go, turn, go straight, turn again. This basically does it all in a smooth motion, and it takes that graph with acceleration, velocity, jerk, but also adds position into it. So that's the positional graph you can see over there of the actual drivetrain moving. Pathfinder generates that on like an actual graph that's using their online library. We'll have the links in the end for you to use, but Pathfinder basically takes each of those positions from the waypoints and the spline, and then uses the gyro, like the Navex, which is what we use, or the IMU, and the encoders to basically make sure that it's constantly using that. One thing to always keep in mind when doing this is that there's always a frame rate, or like in this it's the DT, which is the variable used in the code.
Yeah, your time step.
Yeah, your time step. And basically what that is basically the time step between each position that it goes to. Right. So when it's
and if we go back to the PID controller,
yeah,
it's your DT, right? Because like when you're computing, it's basically doing a different way to calculate the integral and your derivative. So you use your DT as your time step when doing that.
Yeah, and when applying this to the actual code, it's important because when in Pathfinder, basically you can set your own DT, but when you're running it on the FMS, the field management system and competitions, it may be different, and that actually changes the final position of your robot. So keeping that in mind is really important when you're making your paths and then running it on the robot.
Oh, and then one more thing with Pathfinder is that actually before they had, like, so for example, yeah.
Would you use the motion profiling control mode or motion magic control mode?
Okay, so yes, we should have specified that. Thank you. So for our example here, everything is running motion magic except our drivetrain. And our drivetrain, what it's using is it's not actually running on board our Talon SRX. It's running on our RoboRio using the Pathfinder library. And what it does is it has its own basically PID controller. And then we take the output of that and we just call a .set %output method on the Talon SRX, and we pass it that value. And then one more, yeah.
Why did you choose that option instead of using the motion profiling mode on the Talon SRXs? Was there a specific purpose
So
when you separated them?
with the motion magic stuff on the Talon SRX, we found it really good for one-dimensional systems where you have like just an arm, right, or you have an elevator that just moves in one dimension. We didn't find it as good when doing two-dimensional stuff like our drivetrain, just because there's so many tools available in terms of visualization for Pathfinder, and like we literally see the field, we can plot where we want our robot to go, and then it'll generate basically a file that we can put on our RoboRio, and it can read that in. With the Talon SRX though, you have another control mode. It's not motion magic, it's motion profiling. I forget the exact name of the control mode, but that allows you basically to stream motion profiling like points or like trajectories to the Talon SRX, and the Talon SRX will basically it'll run that, so it'll run the trajectories you're passing. Another thing is the Talon SRX, you have the sensor input, and that's good for like encoders, but at the moment, like I believe the Pigeon IMU, I forgot when that came out, but I don't think we had it at that point. So we couldn't connect a gyro to our Talon SRX either. So
would you say that using this Pathfinder library is as good or even better than the Talon's built-in trajectory point streaming?
So this is like subjective, but what I think we would recommend is that you use motion magic for your one-dimensional systems, your elevators, your arms, and then we use Pathfinder, for your drive for autonomous at least.
Sorry, also just to kind of put all this into context, if you go back to our robot kind of example, so if the drivetrain were to use motion magic, the one-dimensional system, the problem with that, it would still take into consideration the velocity and the acceleration of the drivetrain, but if you can see when we go towards the scale, it basically runs that simultaneously, like driving while turning to it, and when you're basically creating the path, it seems like it's not taking into consideration the angle and while it's driving, but it's actually using the NavX with the Pathfinder library. So what Pathfinder actually does is when you're writing the code, it has a tank drive and a swerve drive implementation. And with the tank drive implementation, you really just put the sensors that you're using and the motors that you're using, and it outputs just the value that you have to send to Talon SRX. So they've made it so that it doesn't work built into Talon SRX, like Justin was saying, but you use it separately, and then you provide those values to Talon SRX.
Yeah, and then like just one more thing, like the curvature, like while we're driving, that's not like an open loop problem. That's like we're purposely driving that spline in order to get to the position. And then one more thing about Pathfinder is actually like they had issues before. One of the big ones we found was that you can't drive backwards. There's like a problem with the generation of driving backwards for some reason. There's ways to fix that for Pathfinder 1.0. Also, Pathfinder kind of like violates some of the acceleration rules, because if you drive and then you make a wide turn, for example, in order to do that turn, your right side of the drivetrain actually has to go faster than your left side, right? And because of that, it violates the acceleration of your right side. Yeah. It's kind of weird.
Because of that, when you're using Pathfinder, you'll realize that one big limitation is, like we said, like open loops isn't very repeatable. Pathfinder kind of has a similar situation in the opposite scenario where it's not repeatable because you have to tune it so accurately that when it's basically turning, it has, for example, when we were running around the switch to go to the other side of the scale Pathfinder path on our robot, basically when we do it on a practice robot, which is just a drivetrain, it would go there perfectly, but on the actual robot, once the elevator starts moving up, it would kind of go offset it, and sometimes it would go and hit the wall, sometimes it would go around, and we had to tune it over time. So tuning Pathfinder, the cruise velocity and acceleration with your elevator is also as important as tuning the PIDs.
And then also like Pathfinder 2.0 is actually, I think it's almost out, and that fixes a lot of the issues with the acceleration. Also, I think they're trying to fix the driving backwards. Also, they have just different following methods. So before it's kind of like PID, but they have, I think they're trying to implement more advanced methods. So like 254 in 2017 and this year, I believe, they use something called a peer pursuit controller. And that's just like a different type of controller and that Pathfinder is going to implement. So it's really like following what 254 is doing, and it packages it nicely into a library for you to use.
That picture that you see over there of like the field, that's actually using Lightning Path, which is based off of Cheesy Path, which is basically Cheesy Poof's version of Pathfinder, and they have an online system you can use. We have the link in the end, but that basically allows you to just type in the waypoints of the actual position on the field and a relative points, and then it creates the spline for you. So it even takes away that much work from you.
Okay, so then we're just gonna recap really quick. So we want to reiterate, software doesn't fix all your problems. Like for the tuning, the motion magic and stuff, that only took us 6 minutes to do it, just because we followed that 8 to 10% stall rule, and then makes it super nice to tune your PID. So like that entire elevator, like going to the set position, like after we wrote the code, it took us like 5 to 10 minutes to tune that entire system. Then we don't recommend you use open loop systems. I think it's pretty obvious why you wouldn't, just because it's not repeatable. And then we do recommend you use the Talon SRX. You can do all of the stuff we mentioned by writing your own code, but the Talon SRX is like pretty much developed for you, and you can really use that in like improving your robot's performance, and you can practice, like you can focus on practicing rather than like working out bugs in your.
Yeah, that's a question.
Is there a reason that you especially like mentioned Detail XRS as your speed controller, or like?
Yeah, and that's because we think for like an introduction to control systems, we really recommend that you use a Talon SRX. Otherwise, like in order to achieve the performance of like motion profiling, there isn't really an easy way to do it right now. For PID, if you don't use the Talon SRX, WPILib has the PID controller class, which you can use. It's a similar thing, but it runs on your RoboRio. Thing is, the Talon SRX runs at a higher refresh rate. It's control loops, so we do recommend that. And it also has Motion Magic, which can automatically generate the motion profiles for you. And then, of course, you need to tune your PID loops, and then use high refresh rate sensors. So, like with the vision thing again, like you don't want to use the camera as your feedback sensor. You want to use something with a higher refresh rate, like your gyro. So now we're gonna go through like a couple of examples of designing control systems. So we kind of talked about all of these before, but we're gonna kind of like package it nicely for each like subsystem of your robot. So for something like a drivetrain, we use Pathfinder again just to generate the trajectories, and then the splines allow just our smooth motion. And then the control loops are run with our encoders as feedback, and then also our IMU, or like our gyro, the NavX in our case, to kind of follow the heading of the heading of the spline. And then you can also use other methods of controlling your drivetrain as well, right? So with the example we saw before with the PID loops, you can just use a standard PID controller, like probably 2 separate ones. I think we did that one year, where we ran a PID loop on our rotation and then a PID loop on our encoders. We did that for 2017, and that works as well, right? It's maybe not as nice as the spline, but it definitely can do the job.
Another subsystem, I mean, this is not really a subsystem, but this is more just of a way to improve your accuracy when you're doing closed loops, is using vision. And the way this would really work is you would have what we would use is like in this scenario too, there's like a camera connected to a Raspberry Pi or any kind of system that you need. You could also use a phone which has a camera built in, and you connect that to a network table which goes to your RoboRio. The great part about using vision is basically you, like Justin said before, you don't use it as an input for your control loop. You use it to guide like the NavX and the encoders of where to go. In this example, you can see that it uses turning for vision. So basically, if this was a really great example when in the 2017 game where the reflective tape was there when you're shooting fuel. So then you can basically go and accurately aim at the desired position using an LED light on the reflective tape. It would detect the HSV. So if you're using OpenCV is a computer vision library, if you've heard of it, but basically that allows you to write custom code to do camera vision. So you could also detect things like HSV, that's basically color values using hue, saturation, and then a value, and then that can detect a certain color, like the green color or the green light from the reflective tape. You could use contours to detect different shapes if there's a specific kind of shape you want to do. That's a little more complicated in FRC programming, we really recommend using HSV most of the time because when first comes out with competitions, they almost always in previous years have used reflective tape so
Or
that you can
retroreflective tape.
or retroreflective tape to figure out where the color is. You can also do edge detection, which is a lot more broader, but then if you can find prominent lines and basically write your own algorithm to figure out which lines are useful. And then if you take the angle from the camera to that or the distance from the camera to that, you can basically use those as set points for your gyro or your encoder to use and use that as feedback. So then you can provide that to the Talon SRX. So it's basically just improving the PID controller or the improving the feedback that you're getting from the robot using vision or camera recognition.
Yeah, and then of course you can also use like COTS alternatives, which are like really prevalent now. So like Limelight is one specifically designed for FRC. I believe it hooks up directly to your network table. So like that's like what your smart dashboard runs on. So I'll actually just return you the angle to your goal instantly. Like you tune it, like it's just a small package. You go to its like dashboard, you configure it to detect a certain color, and then it'll literally hook up to your network tables, and then it'll return the angle to your target position. And then you can use our PID stuff to do control loops on your gyro and do the same thing.
Setting up the Pixie is also somewhat, Pixie is the other COTS part, but the nice part about Pixie is you can basically aim it at the color you want, like the retroreflective tape. You aim it at it, you hold the button, and it's already learned the HSV for that, and now it'll always find that wherever you put it. So it's super easy.
Yeah, so I think for like 2017, if you remember Otto's robot, I believe they used a Pixie, but I could be wrong. So like obviously they were probably the best shooting robot in Georgia, so obviously is effective just using COTS parts as well.
Another situation or another subsystem would be using arms and elevators. Like we said before, it's important to use encoders on these and limit switches. Limit switches, like Justin said before, aren't really used in the control loop side, but it's just important to ensure safety. In this example, you can see that we had limit switches on the bottom of our elevator and at the top. So if it were to ever reach the bottom, it would automatically reset the encoder value to 0 and it would start the loop again. This is useful because you might have seen previously, like for example at our Columbus event, we basically had a problem where a robot would go all the way to the max height and start to hit the top of the elevator. This was before we had a limit switch there. So once you put the limit switch, if it would ever hit the top, it would basically switch off the motor, reset it to the bottom place. Once it reaches the bottom of the limit switch, it would start again. So you're basically resetting your control loop and making sure that it's safe and nothing's going wrong with the robot, which increases the life
and
of
then
it.
just to clarify what happened there, what we think was the issue is that like let's say we lowered our entire elevator and arm and like we hit the scale, for example, while lowering it. Then what would happen is like we think that it was drawing too much current, it would trip the snap action breakers, and then our talons would actually turn off. Once they would reboot, it loses the sensor data, right? Because the encoders are relative to its starting position. So if you have a method to re-zero your encoder, because it's relative, then that's really nice like fail-safe to have on your mechanism.
Yeah, and then using for arms and elevators, we used motion magic for both of these, even for our arm to get to different set points. So we have like a scale set point, a switch set point, intake set point, and all of these it works well together because if you need to get from one position to another, you can basically program it so that they work together. So you also avoid things like hitting the scale or hitting a switch while you're driving towards it.
Or like hitting like part of your own robot.
Yeah.
And then another type of controls loop that's common in FRC is like if you have a shooter. So that picture is actually 254 shooter from 2017. And then what you do is you run a velocity control loop. So velocity is a control mode on the Talon SRX. And then that can be used to maintain like constant angular velocity on your flywheel when you're shooting. So that's for more consistent shots. And then normally you use an encoder like on the flywheel and then you measure its velocity. And then you can run a control loop on that process variable. And then one thing that's important to note though is that like closed loop isn't always needed. And actually it can sometimes hurt you. I think 254 in 2017 started with a PID only controller, but because you see their mechanism has like 2 parts for like balls to come out of, like it's like a double shooter. They had issues with the PID controller because it would oscillate too much. So what they did is they used a PID controller to spin up, and once they hit a certain target velocity, they would actually take samples of the data or the output of the controller, and they would average it essentially, and then use a feed-forward open loop to control the shooter. So they were like, basically, I want the mechanism to rotate at this velocity. It sets the PID controller. It rotates at that velocity. Then it takes averages of the outputs of the controller, averages it, and then sets it as feed-forward for the motors running the shooter. And then one thing that you can also do with like control loops and shooters is, let's say you have a game where you have a goal and you can be different distances away from your goal, and you want to be able to shoot from any position, right? So you can actually like map your velocity of your shooter to the distance away from the goal, and then you can have different speeds for different distances, and that can be like continuous. And I believe 254 also did that. Yeah. So now, just like looking back at the initial examples we looked at, we can really like understand like how each system is working now. So with the one on the right, again, it's like all the vision stuff Mannit was talking about, just taking so they have their green light, which is reflecting off the retroreflective tape. Then they're getting the angle difference, and they're setting it on their control loop as like probably an encoder on their turret, measuring the rotations of it. And then they can consistently like aim at the right place despite the motion of their drivetrain. And then with the Spartan Robotics example, so they didn't use like Talon SRX, like they used their own implementation of it. But you can see like how if you use Talon SRX and like Motion Magic, you can achieve something super similar just by running control loops on like encoders on each of the linkages of the arms. And then lastly, just some resources to look at. So with the Talon SRX, there's really great documentation by CTRE, and it walks through like tuning all your loops and everything, like the different control modes, and that's a really good like read if you're using Talon SRX. Then you can check out Pathfinder, which we talked about earlier, which we use to follow our splines and autonomous, and that's version 2.0 linked. It's still in development though. And then we also use Lightning Path, which Mannit mentioned is what we use to visualize our splines when we generate our paths and trajectories. And then the Cheesy Poops has a really nice motion planning presentation that they did in 2015, and it still holds up today. So, any questions? Yeah.
Also, if you want to see any of the examples that we showed, we have it all in our GitHub URL over there. You can just go see our previous year's code, and that basically, like last year's code, has a lot of the examples that we showed throughout this presentation. Yeah. Thank you.
Thank you.
All right, I believe that concludes today's TE. For 5E members, we will be staying